Hey everyone, welcome back, and today let's solve Leetcode problem 3341, titled Find Minimum Time to Reach Last Room Part 1. So there's a dungeon with n by m rooms arranged as a grid, and we're given a 2D array move time of size n by m, where move time at index I, index j represents the minimum time in seconds when we can actually start moving to that room. So we start from the room 0, 0 at time t equals 0, and we can move to any adjacent room, where moving between adjacent rooms takes exactly 1 second. Now we want to return the minimum time to reach the room n-1, m-1, which is basically just the last room in the input list. So two rooms are adjacent if they share a common wall, either horizontally or vertically. So let's go ahead and look at the initial example here. We have a 2D array, or 2D grid, if you will, 0, 4, and then 4, 4. In this case, we have an output of 6. Why do we have an output of 6? Well, because that is the minimum time to go from the room 0, 0 to m-1, n-1. And let's kind of see how that kind of boils out in this problem of length 2. So the reason why the minimum time required is 6 seconds is, of course, at time t equals 4, we can move from room 0, 0 to room 1, 0. And keep in mind, moving to adjacent rooms, they're going to take exactly 1 second. And since we have 4 seconds, plus that 1 second that we took to move to adjacent rooms, at time t equals 5, we can then move from room 1, 0 to 1, 1. That would just take 1 extra second, for a total of 5 plus 1, or 6 seconds. Similarly, in example 2, we have move time to be 0, 0, 0, 0, 0, 0, and in this case we have an output of 3 because that is the minimum time in seconds to reach the last room n-1, m-1. The reason why that would work is still we of course start with or initialize a time of 0, and we're of course moving from room 0, 0 to of course room 1, 0. Since that is an adjacent room, it is time equals 0, and it does take 0 seconds. It's really just 1 second to move to that adjacent room, like the problem statement tells us. And then at times t equals 1, we can then move again from 1, 0 room to the next room of 1, 1. That's also just an extra 0 plus 1, or 1 extra second for that adjacent switch. And finally, very, very similarly, at time t equals 2, we move from 1, 1 to 1, 2, and that's another 1 second for that adjacent room switch, for a total of 1 plus 1 plus 1, or 3 minimum time required seconds. And finally, using that similar logic here to go from 0, 1 to 1, 2, or m-1, n-1, that would be 3, right? That is a minimum time of 3 minus, or rather just 3 seconds of 1 plus 2. So for the constraints here, we see that n and m are both going to be between 2 and 50, where that is the number of rows and columns, if you will, of our 2D grid. And the index I, j in the move time 2D grid is going to be between a value of 0 and 10 to the 9th power, which brings us to the main kind of observations to really make to solve this problem. Now, when we're just kind of looking at the examples and just looking at the problem statement in general, what do we usually, or what, would we think of how to solve this problem, or its structure? Well, let's think about it. We want to go from room 0, 0 to room n-1, m-1, basically just the last room, or the bottom right room, right? Bottom rightmost room. And so how would that kind of look like in theory here? Well, it'd basically just be a very straightforward shortest path problem. But in this problem, specifically, there's a twist. We know that each cell has a time constraint. That's basically like our time gate, right? Again, move time at ij is going to represent the minimum time in seconds that we can actually start moving to that room. That's kind of like that time gate, or that time constraint for each room that each room actually has. We can't actually enter any cell before its specified move time in the input. And so that kind of basically tells us that even if we reach a cell early, we have to wait extra time just to enter it. That's going to affect our total time negatively and increase it, which of course we want to minimize it by basically decreasing it as much as possible. And when I say decrease, I really just mean minimize and add the least, because you can't really decrease the time. That's not theoretically possible, at least in the context of this problem, right? So how do we actually efficiently find the shortest path, from the first room to the last room, or the top left room to the bottom right room in the 2D grid? Considering all these different time constraints for all the different rooms, there's a very common shortest path algorithm, with these different constraints. It's a very common algorithm called Dijkstra's algorithm. I don't know if that's how you pronounce it. I'm going to just try to spell it and comment that out real quick. I think it's DGI, and then you have a straws, I think, or something like that, and then I'll put algorithm. It's a very common shortest path algorithm to actually, find the shortest path in a graph with non-negative edge weights, and we're guaranteed that they're all going to be non-negative as we see in the constraints here. And so basically that's going to align with our scenario where each move is going to take 1 second for all those adjacent switches, and all the waiting times are of course non-negative, really, because you can't physically have a negative time. It's regardless of the unit, it's simply impossible. So how are we going to solve this problem? More specifically, the data structure that we're going to be using on a high level to solve it. Effectively, we're going to be using a 2D array of size n by m, where basically it's going to represent the distance. I can call it distance if you like. Basically, distance at any index I, index j is going to represent the minimum time to reach the cell I, j. Right, and we're also going to have a priority queue here, also known as a min heap in Python. That's going to have, it's going to store tuples rather of length 3, it's going to have the time, and it's going to have the x and y coordinates. It's going to prioritize the cells with the smallest current time, because that's going to allow us to lose or minimize the amount of time that we wait for and the amount of time that we need to cover all the cells, right? It's going to have the smallest current time. Right? And finally, we're going to have a list of directions, or basically just direction vectors. This is actually, optional. You could do this in your iteration and your for loop. It's just cleaner when you do it outside. Basically, it's going to be a list of direction vectors, if you will, to explore all the different 4 directionally adjacent cells. And recall that 4 directionally adjacent cells, that just means up, down, left, right, or 0, 1, 0, negative 1, 1, 0, and negative 1, 0. Those are basically just the offset coordinates of how to go in these 4 different directions from any cell I, j. Right, so let's go ahead and get into the code here, and like I usually do for graph problems or matrix problems in general, I always get the number of rows and columns with the length and index 0 of the grid and store them in 2 variables n and m, and in this case they tell us that those 2 variables are going to be quite literally n and m, and so let's initialize them accordingly. I'll call them n and m. They're going to be the number of rows. How do we get the number of rows? Is basically the length of our input matrix move time. And how do we get the length, or rather number of columns in the grid? Is basically the length of move time at index 0. Right? We're just storing or taking or unpacking, if you will, the number of rows, length of move time, and the number of columns, length of move time at index 0, and storing them in the n and m variables accordingly, just to help iterate through the grid and, calculate or update our priority queue accordingly. Right? So now let's actually initialize that distance matrix. And like I was talking about, I'll just call it dist. I think it's a little bit easier to type out each time, and it makes it a little cleaner. We're gonna be doing something called list comprehension here, and basically the way it's going to work is it's going to be a float of infinity. That's how we're going to initialize all the cells to be, right? And it's going to be times m for every single value, or basically just in the range of n. So theoretically, this is a nested loop here, if you will, because we're multiplying by the number of columns, or rather, columns each time for the number of rows we have to accurately get that 2D matrix of the same dimensions as our move time. It's still going to have the same dimensions of n by m, or effectively, we're initializing each cell in this distance matrix with infinity, and basically that indicates that initially all the cells are unreachable before we start iterating over them, or again, that we want to minimize the distance for all the cells to effectively minimize the distance for the final cell, n minus 1, m minus 1, and so they're all going to be initialized, or starting off with the float of infinity. That just means they're unreachable. We of course will change that as we iterate through our input, right? And now finally, let's actually going to start with our base case here. I shouldn't even say base case, really just a starting point here. We know for a fact that regardless of what our input is, distance at 0, 0, it's always going to be initialized to 0, because this is our starting point. We always are going to set the starting cell 0, 0. We're going to set its distance to be 0 because we begin there at time 0. Right, so we're always going to, that's a starting point. We always have 0 seconds when we start from that cell, and we're also going to have a minimized distance of 0 because we don't have to go anywhere to get to that cell, because we always start at that cell initially. Right, now let's also initialize our priority queue here, and like I said, it's going to have tuples of length 3, and initially the first tuple is the starting cell, so it's going to be 0, 0, 0. Right, indicating basically the starting cell and its current time of 0, and of course the coordinates would be 0, 0. So x and y are both 0, and the starting distance, or the current time rather, is also going to be 0, because of course we don't have to go anywhere to reach that cell, as we already start with that cell. And finally, this is kind of like the optional part, if you will. Initialize the directions array, basically like an offset of coordinates for where to go for each index. Basically it's going to be negative 1, 0, and again these are offsets by the way, 1, 0, 0, negative 1, and finally 0, 1. Right? Very simply put. Now, once we actually initialize this distance array, this directions array for all the 4 possible directions to move up, down, left, or right, again, the 4 directionally or cardinal directions. Now let's actually, begin the main while loop here to actually continuously process all of our indices or nodes, if you will, until our priority queue is empty, meaning until we've actually reached the last cell and minimize the time distance accordingly across, right? And the way we do that in most graph problems and matrix problems very similarly is while PQ is not null, meaning while we still have, or basically we're just going to continue processing our priority queue until it is actually empty. Now, in each iteration of this while loop here, we're going to first unpack the current index or the current node. And again, keep in mind, while unpacking the priority queue, we're going to unpack 3 different values because each tuple that's stored in the priority queue is going to have a length of 3. It's going to be the time, the current time that is, it's going to be the x coordinate, and it's going to be the y coordinate of that current time, and it's going to be basically just kind of extracting it or popping off from the heap queue. So heap queue.heap pop method of the PQ array, right, or parameter, if you will, is really just going to be the data structure that we're popping off from. We're popping off or extracting the cell with the smallest current time from the priority queue. That's the whole reason why we have this min heap here, because the smallest value based on time, the first parameter, the smallest current time, is always going to be stored at the top of the heap queue, and so meaning when we pop it, we're always going to get the smallest current time, or the cell with the smallest current time in each iteration, right? Now the first thing that we have to check is the current cell that we're currently popping off, is it the one that we want? And how do we know if it's the one that we want? If it's basically our ending bottom left or bottom right cell. How do we know that? If xy is equal to the n-1, n-1 cell. So if it's equal to n-1 and n-1. That's, of course, our goal cell here to reach. And so if we reach this in any iteration, we immediately return our time because we finally hit our destination. We're going to return the current time as the minimum time required if we reach that bottom right n-1, m-1 cell, right? Of course, this is only when we reach that cell. In all the other cases when we don't, we want to then begin or kind of continue our processing for all the other regular cells, minimizing our time. And the way we first do that is, if the current time that we're at, if it's greater than distance at xy, we immediately just want to continue. All right, let's kind of unpack what this really means, right? If we've already found a faster way to the cell, to reach the cell and start at the cell, we want to immediately skip processing and move on to the next cell. Why? Because we've already found a time that's shorter or less more efficient, or less time or more efficient to start at this cell x comma y. And so why would we want to have a time that's greater than that to make it slower? That just doesn't make sense. We already found a minimum time, and so if we haven't found a more efficient time to start at this cell, we just continue and move on to the next cell. We skip processing as we want to minimize the time for all the cells to effectively also minimize the time for the very last cell as well. Right? And now here we actually use our directions array to account for the offsets to go through the 4 directionally adjacent cells for every cell in this while loop here. So for every dx, if you will, and dy, you can say offsets, if you will, it doesn't really matter. In the directions array, we're going to get the new x coordinate and the new y coordinate, so ny and nx and ny, to basically be x plus the current coordinate x plus this x coordinate offset, and the current coordinate y plus this y coordinate offset. Basically just exploring all the 4 directionally adjacent cells from the current cell x comma y. Now, in this iteration here, now we want to check, okay, are our new cells, if you will, or cell coordinates, are they actually within our matrix boundaries? Meaning we don't have an index out of bounds or list, error here. And the way we can check that very straightforwardly is if our new x coordinate, if it's within 0 and the number of rows we have, again, the number of rows we have is stored in n, and very similarly, the new y coordinate, if it's between 0, meaning it's non-negative, and it's less than the number of columns we have, we know that this new coordinate is actually within the grid boundaries, the new x and y coordinate, because it's a valid index, and so we can then calculate the earliest time, or our wait time, if you will. And the way we can actually calculate that, again, I'll call it wait time real quick. It's going to be initialized to the maximum of move time at this new x coordinate, nx and y. Sorry, there should be a time, not tome. And it's also going to be initialized to the maximum of that, or just the time, and we're going to then add 1 to that maximum result. Why is that? Well, here we're effectively, calculating wait time. We're calculating the earliest time that we can enter the adjacent cell. And we know we have to wait until move time at nx and ny seconds have passed. Why? Because that's the whole property of the move time, input array. That tells us the minimum number of seconds, or the minimum time where we can actually start moving to that room. That represents the minimum time, and so we always have to take that into factor. So it's going to be the maximum of that. If that's your bottleneck, that's our bottleneck, or just the current time that we're at, right? The current time that seconds have passed, whatever the maximum of that is, because that's of course our bottleneck, and then we just add 1. Why do we add 1? Because we know. Why do we add 1? Well, because we know that moving to adjacent rooms, it's going to take 1 second, and so we have to account for that 1 second like the problem tells us. Moving between adjacent rooms takes exactly 1 second, and so we're going to add 1 to the current move process. And that's the wait time for this current new x and new y coordinate, right? Now, we want to actually check, is this wait time more efficient than we've seen before? Is it faster than what we've calculated before for this new xy coordinate? And the way we can very straightforwardly check that is if wait time is less than the distance array at the new xy coordinate. So distance at nx and y. If it is, we've found a more efficient path and less seconds to this x and ny cell, and so we can then update it. And the way we can update that is the new value for distance at nx and y is now going to be equal to whatever waiting time that we calculated, or just wait time. And now we want to then actually append or push to our heap queue the new cell with its more efficient wait time to the priority queue. And so we're going to do call the heap queue.heap push method here. And we're going to pass in 2 parameters. The first parameter is, of course, the data structure that we're going to be pushing it onto. That's going to be PQ. And the second parameter is what we're actually going to be pushing onto the PQ. That's going to be, of course, again, a tuple of length 3. It's going to be the wait time as optimized, or minimized, you should say, and the new x and y coordinates, or just the x coordinate and the y coordinate, right? And again, basically, if the path if this path that we're currently calculating of the wait time is faster, meaning if the wait time for this is less than what we calculated before, of course it's initialized to float of infinity. Any value is less than the float of infinity, and if that's the case, we want to then update its distance to then be wait time, and then actually add it to the priority queue for further exploration for its 4 directionally adjacent cells. And believe it or not, that's actually it. We don't have a return statement outside of this for loop here, because we're guaranteed to return in this while loop itself if we actually reach, or when we actually reach our x and y coordinate of n-1, n-1 eventually, right? So unless I'm getting any syntax errors here, this should be accepted, and this should be a valid solution, so let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So on a high level, how are we really solving this problem? Let's just quickly reiterate the high-level solution. Effectively, we're efficiently computing the minimum time to reach the bottom right cell of the grid, basically just n-1, n-1, and we're considering both the movement and the waiting times. And we're always choosing the next cell using that min-heap property with the smallest current time, and using that method, we always ensure that we find that shortest possible path that also, kind of aligns with the problem constraints of each cell, basically the minimum time to actually start moving at it. Right? So for the runtime complexity here, it's rather complex because we do have a lot of things going on, a lot of data structures, and a rather complex algorithm here. So let me just quickly type it out here. The runtime complexity is going to be big O of, can't find my open, sorry about that, n times m, that's our first part, and that's going to be multiplied by the log of m times n. Of course, for that heap q factor as well, because that's what we also have to take factor into that for the runtime complexity. And for the memory or space complexity, that's going to be a little easier, really just big O of m times n. Sorry, let me just put the O outside. So let me just quickly explain why and how we actually get these complexities here. For the runtime complexity, we know that each cell can actually be visited and exactly once at least, and for each cell that we visit, we're going to perform a heap operation, and so it's going to be a big O of m times n for each cell that we visit, and then big O of log m times n for the heap operation within each cell, and so it's going to be total m times m for each cell, times the additional log of m times m for the heap operation underneath or for each cell, right? And for the memory or space complexity, very straightforwardly, it's just big O of n times m. Why? Because we know that we do use an extra data structure, or we do use auxiliary memory. We're storing not only the distance matrix, we're also storing the priority queue, and that, or rather, each of them could potentially, worst case, hold n times m elements. So technically, it's big O of 2 times n times m, but since coefficients and constants don't really matter in runtime and memory complexities, it's really just a big O of n times n memory complexity. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.